Here at St. Clair College, it's about you. It's about your passion, your skills, and stepping up to the challenge. St. Clair College has 3 campuses in Windsor and Chatham. It's here where we rise above, where we soar to our full potential, providing over 120 advanced diplomas, degrees, and graduate certificate programs. Our reputation as a premier educator and our commitment to academic excellence is seen in all we do, from programs in community studies and the arts, to engineering technology and skilled trades. With the new Zekelman School of Business and Information Technology, with both a physical space and curriculum to ensure that graduates are the leaders of tomorrow. St. Clair College offers a wide range of activities to enhance campus life, from varsity and intramural sports to the state-of-the-art health and fitness facilities. There's something for everyone. Our students and faculty are an important part of our community. The college's mission of excellence in all we do is shared by faculty, administrators, and staff as they prepare students with careers that will shape the economy of tomorrow. Our relationship is ongoing with graduates that ultimately enrich our current programs for student success. It's here where we feel welcomed and inspired, and where we become work-ready. St. Clair College, it's time to take flight. Rise above the ordinary.
Good morning and welcome to mold making session, part of Emerging Technologies in Automation conference. I'm Vladimir Franjo, Industrial Technology Advisor with the National Research Council Industrial Research Assistance Program. And I started my career 30 years ago as a mold designer. It certainly has been following the industry since. A lot of exciting technologies around mold making, as all the others in these times of new artificial intelligence technologies moving in that we are living. I'm really glad to have a group of speakers today that will present the latest and the greatest, and when it comes to the mold making technologies. The first is Amrinder Singh. Is the engineer at Lincoln Laser Solutions. It's a long-time IRAP client, part of Whitfield Welding, with doctorate in additive manufacturing and over 3 years of industrial experience covering optimizing the process parameters, toolpath planning, developing the feedback control system for defect-free additive manufacturing. Amrinder, welcome. And
good morning, Vladimir. How are you?
Excellent. Looking forward to your presentation.
Thank you so much. I will share my screen now. Yep. Good morning, ladies and gentlemen. Please let me know if my sound or if you can see my presentation, if something is disrupting here. Please let me know right away. Am I loud and clear, Mr. Vladimir?
It sounds good. It looks good.
Perfect. Let me start with the additive manufacturing. So today my agenda of this presentation is to show that how the additive manufacturing has changed our process planning, the way we design, and how we think. My name is Amrinder Singh. I'm Additive Manufacturing Manager in Lincoln Laser Solutions. So without wasting more time, let's start. So the question is, what is additive manufacturing is? We keep talking about it. It is nothing but layer by layer addition of material, just the opposite of subtractive manufacturing, in which we take a big piece and start cutting or start milling. Means like taking the material out. But in this case, we will be adding the material layer by layer by layer, making it bigger, not making it smaller. The question is, when did it begin? Well, this has begun in 1981, so almost like 40, more than 4 years ago now. And the first technique which emerged in additive manufacturing was 1987, which is called stereolithography. I will just go over it. The best part of additive manufacturing, which we do, is it has the ability to produce very highly dense parts, 99.99% we're talking here. Now, there are many kinds of additive manufacturing techniques available. I will classify them in two different parts. One is metallic, another one is non-metallic. My major focus will be on the metal additive manufacturing, but I will just touch base the non-metallic additive manufacturing. Now, in any kind of additive manufacturing, we can have a metal powder, liquid, or wire as a feed source and use it to make the layers. Now, let me just touch base the non-metal additive manufacturing. There are majorly 4 kinds. I don't want to waste more time on it, but just touch base it. The first is called VAT photopolymerization process, in which your UV laser hits the polymer resin and it solidifies. And the platform, it keeps going down when you make layer. One layer, platform goes down, makes another layer, platform goes down, you keep building this big chunk. In the material jetting process, instead of a liquid, you have wires, and then you melt it down to make a liquid, and the same way this platform keep going down. And then we have a liquid binder in this process, which is called binder jetting process. In this one, you have powder bed, and you put a liquid binder on the top, bind one layer, platform goes down, bind next layer, you keep making the part. This is the most famous now material extrusion process, which we can buy at Best Buy or Amazon, where you have ABS or PLA material coming right through the nozzle, where you have a heating element. It heats just below the melting point, and it keeps adding the layer by layer. Now, this is my main focus, will be metal additive manufacturing, in which, again, we have 2 different kinds. One is powder bed, and one which we are specialized, it's called directed anti-deposition process. In the powder bed, you have metallic powder on one side, which is called build platform, and then on left-hand side, you see powder delivery system. So powder comes from the delivery system and goes on the platform and make the layer, and you have a laser coming from the top. So just giving an idea, because I want to focus mostly on my DED system, which will come in next slides. What are the advantages here? Well, the big is freedom for design. Custom-made parts without any special tools. We can use multiple material at the same time to make those layers. For example, you can make one layer with one material and next layer with different material, or one inside and outside, both can be different materials. Repair and remanufacturing. I will show the example and the application more as we go ahead. This is just to give an idea why I'm talking about the additive manufacturing here. Remote access. So people can sit anywhere in the world, make the toolpath planning, just push it out. It can be Mars or Moon, and machine can be there, and you can just give the command and can start right away. Someone can think, oh, it is a very expensive one. It depends. For example, if you keep customizing and you have a complex design, it might not be too expensive in the long run. Okay, the question is, now what can be 3D printed? Let's see. Oh, definitely you can have a cup. How about if we can have a piece of the cup? Oh, yes. How about a fresh heart model? Well, we can now rocket. How about a house? So pretty much we can 3D print in this era everything. So this is what we are specialized in, directed anti-deposition process. What we do is, so we have a coaxial nozzle, we can see right there. And then laser comes from the center of the nozzle. Powder comes from this cone as a conical shape. And then the laser comes from the center, hits the substrate, creates a melt pool, powder goes in the melt pool, and as soon as the whole system starts moving to one side, that melt pool becomes a solidified bead, creating a single continuous bead. And then in this way, you can do cladding or make up parts. Yeah, this is more elaboration here. So this is as the melt pool keep moving, it solidifies, and you see a continuous bead behind the melt pool. Now, before we go ahead, let's touch base the complete system functioning. So we have to have a controller which can control our movements, a powder feeder which can feed the powder to our coaxial nozzle, and the argon gas. So as we are cladding or we're doing additive manufacturing the parts, we have to make sure that the melt pool does not come in contact with the atmosphere. So, for example, iron-based alloys, they can get oxidized very easily, and then we can have a defects in our final product. So that act as a shielding gas. Not only powder, we can use a wire feeding system. Instead of powder, we can use a wire feed system. And then this is called wire arc additive manufacturing, WAM. I'll go through it more as we come. Next slides. So best benefit of directed energy deposition process is that when we make a layer on the top, you can see we just partial melt the substrate or the previous layer, which makes a perfect bond or metallurgical bond with the base material or with the previous layer. Now, we have, in this process, we have 3 different laser processing parameters, which have a key significance: laser power, scanning speed, scanning pattern, powder feed rate. So more the laser power, more the dilution, and higher the layer height. Scanning speed, higher the scanning speed, lower the height. I don't want to go much in detail because I have more to show you guys. I only have 7 minutes left in my time. So as we can see, all those parameters affect our deposition rates. Mostly the layer height is the key parameter which affect our deposition. So the higher the layer height is, you can see we have from 0.05 to 0.1 centimeters. We have gone pretty much like 1 kg per hour. So it's a significant improvement. Now, some might think, it's a slow process. We know we can do it. No, that's not true. It depends. In the DED, we have 3 main technologies available, which I just showed you. Second one is electron beam, and third one is arc plasma and directed energy deposition process, in which we have wire feed rate and then we have a torch. And this is all computer controlled. And this one we can have a layer of 40 thou, and deposition rate can be as high as 10 kg per hour. Now, if we need a thin layer only, and it has to be pretty downtimes to faster, we can do that too. We can use our powder flow process and still have a very, very high speeds of pretty much 1,000 millimeters per second. Now let's talk about dimensional accuracy. Well, laser spot size can go from, in our facility, 0.5 millimeters to as big as 50 by 50. But at this spot size, bigger 50 by 50, we don't do cladding. For the cladding, we have 0.5 to 6. We can do hardening in 50 by 50. And this is how this single layer, single wall created by the system. So I have 5 minutes left, right, Vladimir, sir? Anyway, let's keep moving on.
Yes, 5 minutes left.
Thank you so much for the confirmation. So I'll skip this one, but this just shows that at the same spot size, we can vary the deposition rate depending upon the production. The whole motive of showing you whole mass deposition rate is that there is a flexibility where we can make it faster or slower, but again, depend upon the design and what the material kind is. But there is a range of flexibility of the mass deposition rate. So it's not slow, it's faster. But again, it comes to the part. What is part about? Working in weld. Well, you can make as big as engine nozzles, rockets. In our facility, we have robot can reach 6 feet. CNC, we have 50-inch diameter and 15 feet length. You can see this is what I'm talking about right there, CNC, and this is the robots. Why this technology is so important? Because we can tailor the material properties. So if we need a hard material on a soft one, yes, we can do it. If you need a functional graded material, we can do it too. We can have a different composition of different powders in every layer to make it a functionally graded material. For example, if you have a material which is softer on the top, hard on the bottom, but we can go gradiently harder, not just like from soft to hard, to retain the properties. Application: aerospace, automotive, agriculture, tool and mining, infinite amount of application. Let's go aerospace. This is a 3D printed rocket. We don't deal in aerospace, but if it's a crazy idea, please go for it. We can have a discussion about it. Automotive. So recently we made a hot stamping. We did a cladding with a hard material on the hot stamping die. And just to show you the numbers on the clad was 60, and this is the base material, which is 30 HRC. So we have made from 30 HRC to 60 HRC, and pretty consistently. From agriculture, we had this agriculture part. This is the shape of it, and we put a tungsten carbide onto it using a DED and made that steel 100 times longer than like steel. The tungsten carbide wears up to 100 times longer. So this part has now got 100 times life more than it was before. Tool and die insert. So we can not only do a cladding on the top of surface, we can manufacture things layer by layer too. So this is a perfect example. So we made a die insert here using a 410 stainless steel and made a spiral cooling channel which goes in, comes out, and we made a hollow structure on the top which looks like this. We can repair the parts. For the turbine blades, if you're missing a chunk of it, it can be repaired back up again. Repair and remanufacturing. So not only you can make the things, but the reason I'm showing this repair here is because you can see that if you buy thermal spray, it has a lot of heat affected zone, but by DED, you can repair the same thing having a least amount of dilution and least amount of heat affected zone. Let's talk about 3D printing. Oh, well, we cannot repair, we can have 3D printing from this is a reducer to elbow bending shape, to any hollow structures, to the straight walls. And this is again, just water goes up, comes out here. Recently, we did a production job for water cooling jacket. We had this base, and this is the final product. We 3D printed a cooling lines and the whole structure on the top of this base applied by the customer. And this is some we have in-house project. This was in the furnace, which used to supply the air inside the furnace, the hot air, and we remanufactured it and still working and functional. There's something we made a lifter just to save material for them. I don't have much time to explain, but let's show you a picture here. So any questions for me? I was a little bit faster because I had limited time.
Thank you.
But I wanted to show you, the scope of an application of the additive manufacturing technique, especially the DED, where you have better metallurgical bond, and it has infinite applications. So please let me know if you have any crazy idea in your mind. Thank you so much. I am open to any questions.
Yeah, thanks a lot. Unfortunately, we're kind of running out of time, but the presentation, there was a question regarding the size of parts that you can manufacture, and you have covered that in your presentation, sort of. But maybe you can clarify that, like because your technology is capable of handling large parts. How large?
Yes.
How large of a parts can you handle?
Well, practically we have a 3 meters of robot which can print a 3 meter big part, right? But we can always enlarge our envelope if there's a requirement. But for now, the largest The largest would I say is the 3 meters from as a point of view of our robot. We have a CNC, which, for example, in these two, you can see this is our CNC in this slide. This has an envelope of pretty much, it can go 12 inches higher and 24 inches on the sideways.
Thank you. No, that's great. Any questions, please connect with Amrinder directly. You can chat with him on here, or he can provide his contact as well. It is on a PowerPoint. So feel free to connect afterwards. Thank you again. And we'll move on to a next speaker. The next 3 speakers are actually going to be talking about a common, amazing collaborative project around mold making. The first on is Dr. Peter Wawrow, who's the Director of Research, Innovation and Entrepreneurship at St. Clair College. He's responsible for establishing and managing research program at the college, engaging local industry to work with college researchers and students through publicly funded research projects. Prior to this role, Dr. Wawrow worked in various manufacturing environments, particularly automotive, by applying ergonomics principles to the plant floor and product design. Dr. Wawrow received his PhD in biomedical engineering from Wayne State University. Thank you and welcome, welcome, Peter.
Hi, thank you, Vlad. Let me just share my screen. Okay, is my screen being shared?
It looks good. Just maybe you want to put it in presentation mode.
Okay, there it is. How's that?
Looks great.
Great, thank you very much. So thank you for having me today. And I'm going to talk about an overview of digital twins, essentially. And this was the purpose or the goal of this presentation is to provide an overview and talk about a project that we've been working on. And this is based on a funding grant from FedDev. So it's a partnership between St. Clair College, Windsor-Essex, and in this case, we're working with Laval. We have a number of different partners, but in this particular presentation, Laval Tool has been very kind in being our first case study in this process. So let me start with a basic definition of digital twins. And essentially, it's the virtual representation of a physical product or process. And if that's the definition, and I'm going to hedge my bet a little bit and say that that's not the full definition yet, but we've been looking at these types of digital twins for a long time. So when we look at a schematic or a blueprint or a CAD or even virtual reality, essentially that's the representation of the fit, form, or function, or the virtual representation of the physical part. So I mentioned that we have a physical product or a physical process, and we have the virtual product. Now, what makes it important, what makes this digital twin important, is the connections between the physical and the virtual. So we'll have some kind of communication between the physical and virtual product. So it's not just enough to be a representation, but we need a connection. So what is that connection? And that's data. So now we can expand our definition of a digital twin to say that it's the virtual representation of a product or process using data, and not just any data, it's real-time data. So for example, we can put sensors on a physical product, and those sensors will generate data and then transmit to our virtual product. So then what do we do with that data? So the virtual product has to do something with it, and it provides information. So now we can define or fully define, we can fully define our digital twin, which is the virtual representation of physical product or process using data, and using that data to provide information by analyzing that data. So essentially, when the physical product generates some data from the sensors that's transferred to the virtual product, then we analyze that data, and we provide that information back to the physical product so we can then optimize it. So that is really the essence of a digital twin, is to make sure that there's a constant communication flow between the physical and virtual environment so that we're always optimizing that environment. So what are the applications? One area is product or process design. So, and this is really the main goal of this presentation, and what Linsey is going to present in a minute or so, is basically this is before we have the physical process or product. We have a virtual representation of it, and essentially it's your design of it. And where we use that, in what the case studies are, or where the use cases are, is when we're trying to procure equipment, basically trying to identify where does that equipment or that product go onto the plant floor. And ideally, we would have the ability to manipulate it and work around it, going into the virtual elements of it, so that we can understand how does this interact with our environment. And it lends itself to a lot of collaboration, whether it's collaboration between one company and another company, or a sister company and another sister company, or even within the same company and different departments. We have the ability to collaborate in that virtual environment. Once we have the physical environment, we can then optimize that process. So by putting sensors on the equipment, we can, again, gather data and then analyze that data and optimize what that physical environment will look like. So an example is quality management. So when we have a product that is being produced, that data is being sent to the virtual environment, and it's constantly analyzed to see if there's any difference in the part quality of the different components. So then once we determine that, we can then send the message or information back to the physical environment to say, hey, we need to adjust this. Predictive maintenance is another area. So we can adjust the loads, or we can adjust we can determine what is the wear and tear on the equipment, and we can do that in the virtual environment. So by optimizing or creating scenarios in that virtual environment, we can then optimize that process. And then the last area we can look at is supply chain management. So not only looking at digital twins of your internal processes and products, but looking across the entire supply chain and looking at logistics. So optimizing the flow of products from different facilities. So I want to leave off with a quick example. So this is a tool changer simulation. So the part on the left is the actual physical part, and then the one on the right is the virtual representation. So again, I mentioned product design, and this is where we are at this stage of our capacity with respect to digital twins, is basically creating that virtual environment. So I just want to quickly play this, and you can see how they're very similar in terms of how they operate. So we have a virtual representation of the physical part. So the next steps would be then let's start putting sensors on that physical part, collecting data, and then start generating that information or that data analytics. So with that, I'm going to pass it over to Linsey and have her present the virtual reality aspects of what we had done with respect to this project. Thank you.
Thank you, Peter, and welcome, Linsey. Linsey Pecile is a digital twin engineer at Windsor-Essex and works with Canadian-based companies utilizing Canada's largest publicly accessible virtual reality cave to assist in their virtual reality and augmented reality research and development goals. Linsey?
Hello, everyone. Thank you, Vlad. Excited to be here, excited to present again. Today, we took a hiatus from the conference last year, but prior to the year before, I was asked to present as well. So very excited to be back in here today. As Vlad mentioned, I'm going to be presenting today on the actual virtual reality cave and where we made this project really come to life in the sense. So I work at Windsor-Essex as the digital twin engineer. We utilize Canada's largest publicly accessible VR cave to support local companies in their digital twinning efforts. The research project being demoed today was obviously created for Laval tool, but in collaboration with St. Clair College, as well as Occupied VR, company based in Toronto. St. Clair College Research and Development assisted with the file organization, materials, and the animation in the initial phasing of the project, utilizing Autodesk VRED software, as well as ANSYS VR Experience software. While Occupied VR went ahead and created the GUI code program. And then I took that file, transferred it into the Unity software, and applied the physics and simulation components to be able to run this file successfully in the VR cave. So the following video will provide more insight into that. Hi, my name is Linsey Pecile. I'm the digital twin engineer here at the VR Cave for Invest Windsor-Essex. This is the Laval gun drill. This was created with ANSYS VR Experience software. This was our first test on this software. Laval was nice enough to provide us with the opportunity to work with them and conduct some initial R&D efforts. And the idea was to create a digital twin of the equipment that you would see on their shop floor in the virtual world, which is what we did here. So we started off with this software here. As you can see, it definitely has its features that it can highlight in terms of visualization. And so you can start to see the materials, the textures, the gun drill itself. All looks very nice. We can come right up in here. If I turn this here, and we can start to visualize the mold. We can look inside the mold and start to see all of the cooling, the heating lines, where we can see our hot spots are and where we're going to have mold defects, essentially. So initially, this started off as a digital twin for visualization purposes. And this was all done, like I said, in the VR ANSYS software. From there, we decided to take it another route, take it a little bit further, and create it as a digital twin where we're not just doing visualization. We wanted to create some movement. So we decided to add some animation to the gun drill because this is what was available in the ANSYS VR software. So you can see the gun drill moving up and down, the table moving from left to right, the actual drill piece coming in and out of the drill, the cavity of the mold rotating around on the table, a bunch of various different movements of the gun drill itself. Obviously keeping in mind that these are all individual movements. They don't work as a sequence per se of how the gun drill would actually be running. These are just animation based that were put in to the software. But we didn't want to create movement in the sense of an animation. We wanted to create movement in the sense of a simulation. So to do that, we had to switch to Unity software. Take a look. This is Laval's gun drill in our software Unity. And we switched to Unity for the fact that we were able to create simulations versus animations in Unity. And really what that means is what I'm going to show you here. So when I zoom in and I press this button here, and I go click, and I press that button there, you can start to see that it's actually running through the G coding on the software for the gun drill and running through what you would see on the shop floor. So it's not showing you what I told it to do. It's not showing you like a video game where I tell it to move 4 feet to the right and it actually moves 4 feet to the right. it's actually reading the program G coding of the specific mold and the cut path that it needs to take, and showing it up here for you to visualize in the VR cave before you actually implement it and design it and cut it on your shop floor. So drastically different. It's understanding and taking the approach that if there is a problem, you're actually going to see it in here. Whereas with an animation, if there is a problem, you're not going to see it because I went ahead and just told the program to forget about it, don't worry about it, just do what I'm telling you to do. This is taking the G coding, this is taking the cut program that is programmed specifically for this mold, and it's taking into account, can I do this? Okay, it's looking at the simulation side versus the animation side. So we were able to do this in Unity. We were not able to do this in our ANSYS software that we were utilizing at the very beginning phases of our project. So I'll just move around here so you can see more of the mold. So you can get right up in here. So we do have, just to show you, this is our testing console box at the top here. Underneath of it is the actual mold cavity that would be created after this was done cutting. So I can come right up in here and get really up close and personal with it. And the last part that I'm going to show you today is the behind the scenes of what's happening on Unity and the console GUI coding that was created specifically for this mold and the programming, the cut path that it's supposed to follow, that it's supposed to take. So you can see on my screen is the GUI console. It shows you the different aspects of what you might see on the shop floor in terms of what's running. So in the top right, you have your NC files. So these are all of the different pre-programmed coding that needs to happen and the path that this gun drill needs to take in order for it to cut and drill in the right places and for the right amount of time and at the right amount of speed and everything else that gets programmed into this that tells the machine physically on the shop floor where it needs to go and what it needs to do in order to create this mold. We've taken that and we've put it into our GUI console here on Unity, which then tells Unity what to do so that we can replicate this in the virtual world. So you can see on the left, bottom left, you have your status of, if your coolant is turned on, if you have outside air coming in or not. Those will change as this is running through the programming. On the top left hand of the screen, you also have all of the code and exactly what it's running through at each point, at each given time. Now, this might not mean anything to you, but that's okay. What it really means is that it's following a specific set of parameters, a specific set of instructions, so that this is going to give you the end result that you desired. Thank you for your time today. And if you have any questions at all, please feel free to ask them in the Q&A session. Perfect. All right. Thank you very much.
Thank you, Linsey. And yeah, we don't have a whole lot of time for questions now, but feel free to connect with Linsey on chat. And I'll move on to well, it's a sort of a wrap up of this project with Laval, Jonathon Azzopardi. We've got to see him in the amazing video at the beginning of our session, as Laval is also a sponsor of our event. Jonathon is the president and CEO of Laval International, and Laval is manufacturer of composite parts, prototypes, molds, and provides engineering services. Company is celebrating its 42nd anniversary this year, and is also been an IRAP client for years. Jonathon is also a very well-known community leader, volunteering on several community industry boards like Canadian Association of Mold Makers and Automate Canada, just to mention some. Always a great pleasure, Jonathon. Welcome, and looking forward to hear how Laval benefited from this amazing collaborative project with St. Clair College and Virtual Reality Cave.
Well, thanks, Vlad. Welcome, everybody. I'm just going to do a little test here. Let's make sure everybody can see my screen. And I think you can.
It's looking good.
Perfect. Great. Okay. So, first off, I've got multiple screens. So if you see my head wandering around, that's probably because I've lost track of what screen I'm on right now. But first off, I want to say, you saw the video, you kind of understand what Laval is. Laval is nothing really that special. I mean, from an aspect of being an SME, we're a small company. And I think that's kind of the specialty of this technology, is that a small SME like us is, trying to access new technology. And I think that's the spirit of the whole conference. So, I think it's a great example. The second thing I want to say is that the group that I've had the chance to work with, which would be, St. Clair College and Pierre and his group, and Linsey and Invest Windsor-Essex, and Vlad, was a great experience. So I want to really emphasize the fact that, if you're an SME and looking to expand into new technology, this is the group you want to talk to. And they're just a great group to work with. And they actually approached me with this technology and said, what does this technology mean, and how can Laval use it? And at first, I really didn't know. And I'll be honest with you, this is what I kind of discovered. The first question is, the value of digital twin, right? What is it really? We already use 3D simulations. Everybody should be using 3D simulations. And if you're not, I encourage you to do it. But it's basic technology, right? We all do it. But then they said, can you add virtual reality and digital twin? And then I had to really emphasize, what does that mean to my company, right? Again, I'm an owner operator, right? So I have to pick my investments wisely, right? And I said, how am I going to use virtual twins, virtual reality and digital twins in my own business? Currently today we use simulations for design verification, right? So we all do that, right? We run simulations within our own software, and we kind of see if what we're designing is going to work. And then all of us do cutter path design, right? Which is also a form of simulation right on the shop floor. So we already do this today. And it was really kind of me understanding that the difference between 3D simulations and the virtual world is how the user is immersed into the space. And you can see by the two pictures that I put there on my presentation, you can see that you're right inside the space. And low-hanging fruit that I believe is working remotely. So like us, like most Canadian companies, we have aspirations to, move beyond Canada, right? And move to, other countries. And we believe that working remotely is the way of the future. So we believe that the digital twin in the virtual world will allow us to do this easier. The other thing is to verify and improve performance. So you can see in that bottom picture, you can see Linsey is right inside the designs. So we actually use this technology, and we're going to be using this technology to actually put the engineer right inside their own design. So now you actually can stick your head in the design and see the possibility of an error. And I thought that was actually very useful for our engineers. And we look forward to putting it right on the shop floor. And then cross-department validations. So this is a machinist that is sitting inside the design, right? So if he's drilling the mold and all of a sudden it doesn't connect, or a mold maker is trying to figure out how to assemble the mold, he can actually step into the design and actually immerse himself and control it. And then the last one is virtual training. So most of us buy our equipment from all around the world, right? So most of my machines are from Taiwan or Italy, from Europe. And to be able to actually train with the manufacturer would save you all that time, all that money. And not only that, but as you change operators, right? Because operators are going to move along, or they're going to move within your company. You don't have to go there, and they don't have to come here to train you. So this is low-hanging fruit for us. But it really wasn't this that got me excited, because I believe all this we can do today, and it's really not that amazing. What the future brings for me is what really excites me. And what that is, investing in a digital twin. What are you investing in? You're investing in the opportunities of the future. So really what I'm looking forward to is working inside the virtual simulation. And if we can work inside the virtual simulation, we're going to make changes inside that space real time. Now, why is this important to an owner operator who's trying to operate his business in manufacturing today? Is because merging digital twins with predictive analysis is going to allow us to automate design. We're in a space now where, designers are hard to come by, right? This is a space that we need more designers. If we can automate the design process, this is going to make us more effective. This is going to allow our designers to be able to do more because we can automate that design because we've combined the two technologies in the virtual space. Then once we get good at that, we're going to combine artificial intelligence with machine learning. And that'll give birth to analytics that will give birth to living digital models and simulation. Now that's a big word, right? Living digital models and simulation. But I put two examples on my slide just to give you a simple and then a little bit more complicated design. So we have a simple electric motor, right? And these are something we depend on all the time. But if we can figure out how to make that a living model to understand if it's going to fail or if we can improve it, or simple design changes that can really augment its efficiency, we do that in the digital world. And then the last thing, I gave you a really complicated example there of, let's say, an automation assembly cell. And that cell is very complicated and difficult, but if we could do it in the simulation world, we could avoid a lot of errors. And this will unlock maximum performance for human and computer interaction. I know I'm right at the time, right, Vlad? So I'll leave it at that.
And I prepared some questions for you, but you answered them in these were really my questions that you covered brilliantly. I do have one, maybe just to help everyone, because I've been at Laval. I know how large your molds are, but maybe that's hard to sometimes transfer via video. So how large are your molds that you manufacture?
Well, that's a great question, Vlad. Thank you. We build some of the largest molds in the world, and the last one we just shipped was actually going out at about 180,000 pounds. And the amount of steam lines that are in it are literally thousands of inches. I think we were at about 16,000 inches of steam lines in one mold.
And this is where virtual reality also can play a role. I mean, these are large products. You may want to do it virtually before you get into making the real thing. That's yet another application around if anyone's making something very large, certainly worthwhile connecting with VR Cave and St. Clair College. Well, thanks, Jonathon. We're right on time. We have our keynote on the main stage coming now. I think the introduction is just starting, and I'd like to again remind everyone to connect with speakers if you have questions, if you're just interested in working together, and see you at the main stage. Thank you again. Bye.